I am on different equipment. So whatever happens today is going to be a bonus. Let's get started. And this is Monday. And it's November 16. And this is our class session. So all the ordinary toys that I got, like Desmos and stuff, that may not be easily accessible. In which case we'll make do with our calculators. Okay, that pen's all worn out of ink. So let me bring a couple more over here. I can at least give you an outline and give you a lot of good illustrations. A lot of good examples today. So we are working in week 12. Yeah, whatever I did, I'm in trouble, aren't I? And I went into the dentist and oh my goodness, I haven't even told you all the bad things that happened today, which you've got all the same problems too. We are dealing with first parametric graphing and combining sine and cosine waves. I can bring more people into the room. Got it, got it. So this is not terrible, except I just have to keep my eye on a different screen. And I can't do the Desmos sharing immediately. So this material right here, we're in section 6.4. And then we're going to open up chapter 7. So I think today we're going to stay in 6.4 mostly. In chapter 7, we're going to be working with something many of you have been trying to use along the way, and sometimes it works, sometimes it doesn't. The law of sines and cosines. And that is solving triangles that are not right triangles. So far in the class, even though some of you have done some experiments with this, we have only done solving of right triangles. You know, if I give you two sides, you find a third. If I give you one angle of a right triangle besides the 90-degree one, then you can certainly find the other one. So you have total knowledge of right triangles, but we haven't formally done other triangles. So that's the mission from 7.1 and 7.2 this week, and then the rest of chapter 7. But let me give you an example, because the things I'll do today will help you directly on your written homework number 10. So let's look at a couple problems in 6.4. And I can bring this to the calculator, and maybe it's not a bad idea to show you how to do some of these things on a calculator. So let's say that, and this is a problem I'm going to take from the book, 6.4 number 3, just to warm up on. Let's say I want you to graph this combination of functions, and I'm going to use a special word, parametrically. So the instructions in the book would say, eliminate the parameter t and sketch graph. But I'd also like you to be able to, and you could just as easily do this in your calculator as well, graph these parametric equations. So let me tell you what those words mean, and then we'll graph this, and we'll graph it inside your calculator, because that's what we have available to us right now. So usually you're used to graphing things like, a line 3x plus 2y is 7, or y equals x squared minus 4. Usually you're graphing things where you pick a value of x and you get a value of y. And you create some function by plotting points x and y. And we can still do that here, but in this problem, in this first batch of problems in that section, they're describing x and y in terms of a third variable. And this third variable, t, in this context, is called a parameter. Parameter in plain English just means the thing I'm using to describe the other things. I'm using t to describe x and y. And you know what the variable 3 times, or you know what the function 3 times cosine of t looks like. You know what the variable, or the equation 3 times sine of t looks like. But what if I'm using this to describe the position of my point in the plane in this traditional graph? So this graph is not the graph that I'm working on this problem. I'll just label this a traditional graph. And then let's work on the one on the paper here. Now I also have to keep my eye on keeping my paper on the screen. So I'm going to do the best job I can of keeping everything on the screen, recording it. But as usual, I don't mind if you just pipe in and tell me if I'm got my paper uncentered or not showing. So think about the different values of t that you have here. And each value of t in this choice, in this table, will create a different value for 3 cos t and a different value for 3 sine t. And I kind of have a feeling for what kind of t's I could pick. Sine and cosine repeat every 2 pi. So I'm certainly going to try to start at 0, maybe into 2 pi. And then pick regular points in between, like halfway pi, pi over 2, 3 pi over 2. Let's start just with those. Now I'm going to repeat to you the values of sine and cosine that I know by memory. And you should have these values also memorized. These are the quadrantal values. So I'm not going to do the calculation here. I'm just going to tell you what sine and cosine are when t is 0. So cosine is 1, so this would be a 3. Sine is 0, so this would be a 0. Likewise, cosine of 2 pi would be 1, so this would be a 3. This would be a 0. That would be back to start. At pi, the cosine is -1, so this would be a -3. And at pi, the sine is 0, so this would be 0. At pi over 2, the cosine is 0. And at pi over 2, the sine is 1, so 3 times 1 would be 3. 3 pi over 2 cosine is 0. So 3 times 0 will be 0. And 3 pi over 2, the sine is minus 3. Let's at least look at these points. And I'll mark them in a different colored pen. And I'm going to mark them very crudely before I go to my calculator. And that is X and Y columns are these last two columns. So I mark 3 and 0. That's where I started. And then I moved to 0 and 3. And then I moved to minus 3 and 0. And then I moved to 0 and minus 3. And this last thing, I come back to 3 and 0. And if I had to make a guess from this point right here, I would say I was circling the origin at a distance always of 3 units from the origin. Now I could add other values of pi in here, other fractions of pi. I could try pi over 4. Pi over 4, cosine of pi over 4 is 1 over root 2, about 0.7. So 3 times that'd be about 2.1. So pi over 4, which would be this location, I'd be a little bit above 2.1. That certainly bolsters my circle idea, but this is only an estimate now. 3 times 1 over root 2 and 3 times 1 over root 2. 1 over root 2 is about 0.7071. That's why I'm calling this about 2.2 or 2.1 approximately. Okay, if I did those symmetric points about the origin, I certainly look more like I'm driving on a circle. And if you think about this, every time I plug in a fraction of pi, I'm just going to be at a different location on the circle. Is there another way I could prove to you that these two functions together construct a circle? Well, I know the equation of circles in general, like x squared plus y squared equals r squared. And in this problem right here, it appears that I'm using or drawing a circle of radius 3. So this circle that I've drawn in red in the traditional sense is x squared plus y squared equals 9. I could show you that that's what these equations create just by inserting my formulas. X equals 3 cos t and y equals 3 sine t. Got to bring another person in the room here. Got it. Okay, what happens if I write 3 cos t and 3 sine t in place of the x and y? Square both of them. Then I get what? 9, I'll raise my paper, cosine squared t plus 9 sine squared t. And that's 9 times cosine squared t plus sine squared t. And by my famous Pythagorean identity, cos squared t plus sine squared t, if I use the same argument, I get cos squared plus sine squared is 1. So this is 9 times 1, or 9. So when I plug the x and y values in there, I do get 9. I do get x squared plus y squared is 9. So that's giving me another strong evidence that this pair of equations, these parametric equations, x equals 3 cos t and y equals 3 sine t, give me a full circle. And I'll draw this on a calculator in a second, but I'm kind of curious if I could speculate, what would happen if I change some of these numbers. Do you see that the x value is waving back and forth between -3 and 3? And the y value is also waving back and forth between -3 and 3. If I changed one of these to a 5, what would that look like? if the X waves back and forth between -5 and 5, but the Y stays between -3 and 3. I might still be creating a cycle. I might come back to where I finished and restart, but perhaps I would create a stretched out circle. That would be an ellipse. So I could try that on the calculator. Let's try a calculator where I have X equals 5 cos t and Y equals 3 sine t. Would that create a squashed circle? Okay, well, now it's time to bring in the calculator. So, and for those of you who are just joining us, the reason we're going so low tech with the calculator is that I'm having some technical issues with my computer. And so I'm not having access to all the ordinary stuff like Desmos and so forth. You could play with Desmos on the side. But let's take a look at my calculator screen. Now, we've made adjustments before, degrees, radians, things like that. And you do that under the mode key, which is second row, second button over here. So let's look under the mode key for just a second. I see my radians and degrees. I think in this problem, since I was using fractions of pi, I definitely want to use radians. So let's get that set. But the thing I want to check right here is down here, function parametric polar sequence. We're using this word parametric. Maybe I want to create this setting and set this on parametric here. Let me change that to parametric. And then show you what the Y equals menu looks like right here after I do that. I need a different color pointer. So let's leave this screen and look at the Y equals menu. Now it's giving me not Y1 equals, but here's X1 equals Y1 equals. And it puts a little T right there. And there is a T variable on my keyboard, third row, second key. So it's almost like it's inviting me to type in two formulas. Let's type in those two formulas that I had just worked on. 3 cosine t. Now, to type a t, I'm going to use this third row, second button, the variable key. It uses whatever variable is appropriate at the moment. So when I type that, I get a t right there. And here's comes a 3 sine t. Okay, good. Got everything on the screen. Close parentheses. Now let's do what we would ordinarily do for a window, right? I said that I ran that t from 0 to 2 pi. Now it looks like the screen's already prepared me to go from 0 to 2 pi. Pi is 3.14 and change. 2 pi is 6.28. The t step, it's going to look at angles every fraction of a pi here. I don't know what that fraction is, but for the moment, it looks exciting. It looks normal. I better be careful with my X screen, Y screen. So I wanted to show X from -3 to 3 and Y from -3 to 3 at least. Let me type in -4 to 4. And this is not going to be good, but make it X scale 1. It'll give us a good illustration of something going wrong. Y scale 1. Okay, I've got some basic settings in here. Let's graph. First response is, well, at least it made a full circle, but we're a little bit upset because we expected a circle, but you count your scale here. 1, 2, 3, 1, 2, 3. You know, this is a circle, and unfortunately, since this screen on my calculator is not naturally square, it's squashed the circle to fit the screen. Now, the way I can check that is under the zoom key. I could make the calculator draw the square units. So let's try zoom 5. Zoom square. I'd like to see a beautiful circle. Okay, now I got my circle. And now I got the scale, 1, 2, 3 on the x-axis, 1, 2, 3 on the y-axis. So parametric graph is something that the calculator can draw for you as well, as long as you put yourself in parametric mode. Let me go back to my graph. How about that thing I said a second ago over here on my paper? What if instead of 3 cos t, 3 sine t, I went 5 cos t? Let's let the x slide back and forth between -5 and 5. Now this time I should get a properly squashed circle in the nice 1-to-1 units. Let's try it. Now that is not a circle because you see my scale, 1, 2, 3, 4, 5 on the x-axis and 1, 2, 3 on the y-axis. So this is actually, and I don't think you want to say it like that, but it's like a circle with 2 radiuses. That's not reasonable to say a circle with 2 radiuses. I'm also monitoring the chat here while we're hanging out, but I can't do that as quickly. So you can still show stuff in the chat window and my screen will still tell me. I just got to keep my eye on that screen. Okay, so this is what happens if I do 5 cosine t and 3 sine t. Notice when I graph this that it's starting over here at 5 and 0. If I regraph, since nothing new has happened, pressing the regraphing button doesn't give me anything, but I'll show you a different way to show this. What if you typed 5 cosine t and 3 sine t in this second graphing, but I changed the way it graphs. So over here on the left-hand side, it's going to be red. Okay, I like that. But that solid line, let me change that solid line to some kind of animation. So you hit enter while that is blinking. And red, I'll take it, but I want to change that line, put my cursor down here, to an animation. Now, I'm not getting good focus on my camera right here. I'm not getting good focus on my camera in either case. But you play with that setting till the line becomes like a little ball. Now let's try it. Okay, accept it. Did I accept it? I did not accept it. No, I did not. Okay, now I accepted it because it's got that little ball icon right there. Watch what it graphs now. Okay, that's actually not too bad, except it flashed so quickly on the screen, I don't think you saw it. Let's go back to the window and then graph. There's a little red dot on my screen, and it's not showing up nicely on the camera, but the little red dot traced this whole thing one time and then stopped. If I change this window to 2 pi and change it to 4 pi, see if you can, I'll hit graph now. and see if you can watch that little red dot kind of orbiting on that blue curve. There goes the red dot one time around. There goes the red dot two times around. It's like barely visible on my camera recording here. But that just shows you how this thing was being traced on the screen. Okay. Let me try another one before I get to the really important one today. What if I wanted you to graph this? Look at 14. I'm in section 6.4. And what if I asked you to graph x equals 4 sine t minus 5 and y equals 4 cos t minus 5, minus 3, excuse me. And the instructions here. Graph the parametric equations. And his instructions in particular say, by eliminating the parameter t. Now I'm going to do it with and without eliminating the parameter t, but let's think about this first before I try to get rid of it. If it wasn't for the 5 and the 3 right there, I'd say, okay, maybe this is a circle of radius 4. Maybe it's starting at a different place. When t is 0, I'll get x is 0 and y is 4. So maybe this would be a circle of radius 4 that starts here and then goes all the way around. That's kind of a crude circle. And that's without the 5 and the 3. This is going to wave back and forth between 4 and minus 4. This is going to wave back and forth between 4 and minus 4. I wonder what the 5 and 3 would do. So instead of x being from minus 4 to 4, what happens if I subtract 5? I literally subtract 5 from every x. Then I'll be going from minus 9 to minus 1. If you think about it, x will be going from minus 9 to minus 1, but it'll still be varying with an amplitude of 4. How about the y's? Ordinarily, without that 3, you'd be going from minus 4 using cosine all the way up to 4. But now I subtract 3 from every y. Now I'm going from minus 7 all the way up to 1. So let's try to visualize this. And then we'll draw it on the calculator and on the paper. So my x is going to be going from minus 9 to 1 minus. So I need some more space for my x here. Minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9. There's a minus 9, there's a minus 1. Notice the center right there is at minus 5. Let's try the y coordinates. I have to go down here a little bit. Y goes from minus 7 up to plus 1. There's a plus 1. Minus 1, 2, minus 3, minus 4, minus 5, minus 6, minus 7. Here's a minus 7. Notice between 1 and minus 7, halfway will be 4 steps, and that'll be minus 3. That's that minus 3 right there. So my drawing is going to be stuck in this box from minus 9 to minus 1 on the x-axis, from minus 7 to positive 1 on the y-axis. I drew a lot more x-axis and y-axis than I needed. But it's going to be what? Centered at -5 and -3. And it's going to start up here and always circle with a common radius of 4. So when t is 0, I'm at this point. When t is pi over 2, I'm over here. Because when t is pi over 2, let me see what direction I'm going. What happens when t is pi over 2? The sine of pi over 2 is 1. 4 times 1, that'll give me a -1 on the x-axis. So I'm going to be going this way around the circle. I'm going to be driving around the circle this time clockwise. So try out some other points right there. That'd be nearly 2.8, 2.8, 2.8, 2.8. Let me see if I can draw a fair circle in here. Well, it's not a beautiful circle, but I can thicken it up, and that makes it look more regular. So I'm driving around this circle in a clockwise fashion. This is what happens when t is 0. This is what happens when t is pi over 2. This is what happens when t is pi. This is what happens when t is 3 pi over 2. And then I'll get back to start at 2 pi. I definitely want to draw this on my calculator screen, right? And I want to draw this centered at -5 and -3. But let's see if I can follow his instructions about eliminating the parameter. In other words, I just want to focus on the 4 sine and the 4 cosine. Let's add 5 to both sides. X plus 5 is 4 sine t. Add 3 to both sides of the y equation. Y plus 3 is 4 cosine t. What do I get if I take x plus 5 squared and add y plus 3 squared? I'll replace the x plus 5 and the y plus 3 on my paper with 4 sine t and 4 cos t. Square that. Square that. And this gives me 16 sine squared t plus 16 cos squared t. If you factor out the 16, then you recognize your Pythagorean identity. Sine squared t plus cosine squared t. Let me advance the paper a little bit. I'll keep this paper on the top of the screen right here. Okay. So I got 16 times sine squared t plus cosine squared t. That's 16 times 1. So what did we just find out? This is a circle of radius 4, centered, let's call this center point x naught, y naught, at -5 and -3. So if I draw this on the calculator screen, am I going to see just like this? Am I going to see this exactly like this? Now I'm going to have to give myself some space in the calculator screen. How about planning ahead? -10 to 10, whatever that is. How about -8 to 8? So let's run our x from -10 to 10. Let's run our y from -8 to 8 and see what that looks like on the screen. Okay, calculator, come back. Let's get rid of these objects here. And let's type in, as I wrote on my paper, 4 sine t parentheses -5 and 4 cos t -3. Let's check our window. I think 0 to 2 pi is going to be sufficient. That'd be one full cycle. So I'll just leave 2 pi right there. Notice the calculator immediately converts that to 6.28. Step size is not really critical. I could make that 0.1 and I would still get plenty of good dots. But here, x min, x max, I want to change from -10 to 10, count by ones, and from -8 to 8, count by ones. This is going to screw up my squareness. I don't think my screen is going to look perfectly square like a circle, but then I can always do zoom square again. Let's just try and see what happens. Hit the graph button. Okay, it is drawing a circle. It is drawing a circle down in the lower left. I could check the center of that circle, but first let me make it square. Zoom square, number 5. That looks more like a circle. Notice the very tippy top. It didn't exactly finish the circle right there, but that doesn't really bother me. I could use more time if I want to. How to show this on my calculator screen. Where is the center? 1, 2, 3, 4, 5. And down 1, 2, 3. I can draw on the screen without doing too much damage, because I can just wipe it off. But it doesn't show that dot exactly where I want to center it. Let me take it off screen. Draw as I look at it carefully. I don't recommend this, by the way. Don't draw on your screen. It doesn't come out exactly where 5/3 is, because it doesn't come out exactly on that dot unless I tilt it in a funny way. Well, it seems I can just wipe that off the screen, but I don't want you to take any unnecessary risks with your screen. So especially on the old style ones, I don't think you want to draw on that screen because it's not a shiny screen. Okay, but just a gentle soap and water might remove it if you have a problem like that. Okay, this is one form of graphing that we want to do in section 6.4, but this is not the key form of graphing that I want to show you today. Let me move the calculator. Let me bring in the book and show you the problems that I'm really interested in. So these problems right here, from 27 to 32, they are like problems in your homework, written homework number 10. So let's do one of these. Maybe we can do 2 of them. What would happen if you add a sine wave and a cosine wave? And let's use the same argument. Sine of x, cosine of x, or sine 2x, cosine 2x. There's a general rule in trigonometry that says when you add a sine wave and a cosine wave of the same argument, of the same function variables, then you just create another sine or cosine wave. Let's type it in the calculator first before I show you how it works. What if I typed in sine x plus 3 cos x? Okay, so I'm going to write this on paper here, just so we're oriented, because I'll still scan these papers when we're done today. This is sine x plus the square root of 3 times the cosine of x. This is problem 6.4, number 29. Graph as a single sine wave That's what the instructions are in the problem. But first, let's type this in and see if it looks like a sine wave at all. Okay, I'm going to keep my screen a little bit farther away here so that I can focus on the equation and the screen. And I was just playing with this parametric stuff, right? So let's get out of that mode. I'm going to go back to function. Sitting here in the basement, and the cat is at the basement window crying to be let in. If you hear a little meow in the background, that's what's happening. Okay, function mode, y equals. Let's clear out this other one. Oh, while I'm here, why don't we make this red so that I don't have to deal with that immediately. Good, and good, and good. Okay. Graph these two functions separately, sine x and root 3 cos x. So I type sine x. Oh, sorry, I have to get my cursor over here. Sine x. Notice I'm not in parametric mode anymore. The calculator automatically goes back to the y equals menu with x as a variable. And let's type in square root of 3 times the cosine of x. And you're fairly comfortable with what those look like. You know what a sine wave looks like. You know what a cosine wave looks like. And I've made an amplitude of root 3, which is about 1.7. So let's graph these and let's find a decent window. In fact, before I do that, why don't I just zoom on a decent window? Let's just zoom on a standard window. If this needs to be adjusted, we'll adjust that. There's the first sine wave. Blue. Here comes the cosine wave in red. Now that's not too bad. And that cosine wave has an amplitude of nearly 2, which is about 1.7. I think what I'm going to do is let's just redraw this only from 0 to 2 pi. And let's get rid of some of this dead space. So x 0 to 2 pi and y, minus 3 to 3. X is 0 to 2 pi. And we'll count by x scale pi over 4. That'll give me a nice equally spaced marks. Say minus 3 to 3 on the y-axis. That sounds fair. We can change that if we like, and graph. So I want you to see just one sine wave, just one cosine wave. The cosine wave, though, has a higher amplitude, about 1.7. Now, this is what I want to illustrate, and then I'll show you how to do this calculation yourself. What would happen if you added that blue wiggle and red wiggle, physically added them, every point, I add the blue point and the red point, what would you get? So my promise to you is that when you add these, you get another sine wave. The difference is it might have an amplitude different than these two amplitudes. Might have a different period too. We can check that out. Although the positive part is the period is going to stay the same as the period of these two. But it might have a different starting place. And the starting place is when you set this argument equal to 0, solve for x. The starting place is minus c over b. Let me just add these two together. Now I could add those two together just by typing them into each other, I could also add those two together by telling the calculator to add y1 plus y2. If you haven't seen that before, it's kind of handy. Function variable y1 of x. To type in the x part. Plus function variable. The variables key is right here. 4th row, 4th button. Y variables. Function variables. Those are the y variables. And I'll just type y2. Good. Of x. And this will add those two functions together. Watch what you create. Oh, and notice it'll be drawn in, it looks like it'll be drawn in black. Going to see the whole thing for effect, but that looks like another sine or cosine wave. Now, I'd like to see a larger picture of it, but it looks like one period. See, it like started below peak, hit valley, and then came, and it was trying to get back to peak. It looks like a sine wave. Now, maybe the starting place is different than the other two starting places. Maybe the amplitude is different than the other two amplitudes. But notice the period is about the same. It looks like I did one cycle in 2 pi seconds. I want to see more of this. So I'm going to go over to here and say, how about minus pi over 4 to 2 pi plus pi over 4? What would that be? 9 pi over 4? I'll keep the same pi over 4 marks on the x-axis. I just want to see a little more of that curve. Okay, here comes the sine wave. Looks like I grabbed a great deal more of that curve. Here comes the cosine wave. And then when I add the two together, I get this new wave. Notice also it's drawing a little bit slower because 1 point at a time, it is drawing the red plus blue. The way I wrote it, it's drawing red plus blue 1 point at a time. Notice the amplitude looks nearly to be 2. Now we could try and see if we can find out exactly why. But this is a comforting thing. This is something I want you to file away in your mind. When you add or subtract a sine wave and a cosine wave of the same argument or of the same period, here these both have a period of 2 pi. So I'll say it both ways. Of the same argument or period. You always create another sine or cosine wave of the same period. You always create another sine or cosine wave of the same period. Okay. Sorry about that. I got a phone call coming in, which I got to decline. Excuse me, let me reset my camera. That hasn't happened too often, but once in a while. For some reason, I'm using my phone as a camera and it doesn't block the phone calls. Okay, let me get rid of that list right there. There. When you add or subtract a sine wave and a cosine wave of the same argument, that means x and x, 2x, 2x, 3x, 3x, any matching argument. Now, notice if these arguments are the same, it has the same period, so you could also say it that way. You always create another sine or cosine wave of the same period. So maybe period is the word I should prefer. Let me show you how to do it, and then we'll match that against the drawing we just did. So take your expression, and I'm going to write it with lots of space so we can work on it. Plus root 3 cosine x. And it's like I have a times sine x here and b times cosine x here. You know, the a is the amplitude of the sine wave. And here the a is 1. The b is the amplitude of the cosine wave. And here the b is root 3. So first do this change right here. And he illustrates this very nicely in the book. If you want to see him repeat these calculations again, I'm going to give you the exact example. He does this calculation that I'm about to show you in example 4. So let me write that down. See also example 4 in this section. Okay. So take the a squared plus the b squared. Now, a squared is 1, b squared is 3. So a squared plus b squared is 4. And take the square root of that number and get a 2. And then let's adjust these two expressions by writing a over a squared plus b squared sine x plus b over the square root of a squared plus b squared times the cosine x. Now, as it is, I've changed the problem, right? So what I'm going to also do is, okay, I'm going to get rid of that message. Let me dismiss that. Okay. So since I've actually divided each piece by the same thing, square root of a squared plus b squared, let me multiply the whole mess times the square root of a squared plus b squared. Now I haven't changed anything. Now the problem is I wrote it much too cramped. So to make this nicer, I'm going to rewrite it with generous use of space. Compare this to what we originally wrote, a sine x plus b cos x. This is exactly the same thing, except I've just divided the inside by a squared plus b squared square rooted and multiplied the outside. If I multiply this purple square root of a squared plus b squared through here, I still get the sine A sine x, B cos x. But let's put in this A and B right now. So now I got y equals, and I already said the square root of a squared plus b squared, in this case, came out to be a sweet number, just a 2. And the a over the square root of a squared plus b squared. Now a was 1, and the square root of a squared plus b squared was 2. So let me write that as sine x, that's that piece. And then this piece is 1 over 2. I'm heading for a special identity. So I wrote this piece over here. I wrote the sine x piece first over there. Let's do the same thing with these 2 pieces right here. Say, I'm going to repeat cosine x first. And then what is b over the square root of a squared plus b squared? Well, b was root 3, and the square root of a squared plus b squared turned out to be 2. Now let's look at this expression right here. Already you see things forming according to the graph that we drew. Do you remember the graph we drew appeared to have an amplitude of 2? I got a 2 outside here. Maybe this is a sine wave of amplitude 2. How could I recognize this right here as a single sine wave? Let's think about my trig identities. I got a trig identity that goes what? Sine cos plus cos sine equals what? The sine of an angle plus an angle. Now here I don't know what angle I have right here, but I have an angle. Let's call it C. I have an angle whose cosine is 1/2 and whose sine is root 3 over 2. That's something I could potentially draw. So this is 2 times the sine of x plus c. That's good. This fits the amplitude that my calculator showed me. It fits the period my calculator showed me. In other words, the 2 original functions had a period of 2 pi, and so does this one. But it's got a new starting place, this plus c. My camera right now seems to be kind of lagging or frozen. I'll have to see how that recording works. So I'm not getting a good view on my screen here. That's a little bit better. What is this C? Could I figure out what angle that is right there? Well, I have to draw an angle that has a cosine of 1/2 and a sine of root 3 over 2. Let's draw that. That's a famous angle. Cosine 1/2, that's 1 to 2, adjacent to hypotenuse, and sine root 3 over 2. That's famous angle. That's 60 degrees. Or if we prefer radians, it's pi over 3. So what have I discovered? When I add the sine wave and cosine wave up here, it looks like I create a sine wave of amplitude 2 that starts where? At minus pi over 3. Phase shift minus pi over 3. You get the phase shift by setting the argument equal to 0 and solving for x. which here is not so bad because there's no other numbers involved. But this is something I can test. I can type this in the calculator and see if it matches that same graph that I drew. Let me move that paper up so I can type this in the calculator. Now there's my 3 curves, right? Let's turn off this curve right here. You can just turn this off by putting your cursor on the equal sign and hitting enter. Now you got that curve turned off. But let's type in the curve we just calculated. 2 sine, sorry, get my cursor to the right side of that equal sign. 2 sine x plus pi over 3. The moment I type that, and I'm thinking to myself, okay, I better make sure I'm in radians. Let's go check my mode. I am in radians. Okay, that's good. Let's go back to here. Let's raise this calculator. And now let me see if that graph, which is going to be green, matches the graph I produced a second ago when I added y1 and y2. Clean off the screen a little bit. There we go. Let's graph. Here comes the sine wave. That's the y1. Sine wave, amplitude 1. Here come cosine wave, amplitude √3, about 1.732. Here comes the sum of the two. Now, this is not showing up excellently on your camera, but it's being drawn green. Now that was the formula that we just discovered, which is up here, the 2 sine x plus pi over 3. Let's go back to the y equals screen and turn on that middle function where I summed them. Put your cursor in the equal sign, hit enter. And while I'm here, should I make this thick black line? Okay, it doesn't much matter. I guess I'll make that line thick. I think that's the same thick as all the others. Okay, let's try it out. Now the problem is I already got something drawn in green. Now I'm going to draw it in black. I don't know how that shows up on this screen. Let's find out. It's not too bad. You see the black color is being drawn over the green color, but it's not beautiful. But at least it appears to be a perfect match. Here's the black color being drawn over the green color. Okay, let me show you the calculations again, how I did that, because that's a really valuable calculation. I started out with 1 times the sine of x plus √3 times the cosine of x. And I changed that into 2 times the sine of x plus pi over 3. And I changed that using this trick of multiplying and dividing by 1 squared plus √3 squared. And rearranging this using the identity for the sum or difference of the sine of 2 angles. That's too crowded. I'm going to have to illustrate this again. Now, I could use other identities. I could have created a cosine wave. I could have created a sine wave with subtracting an angle here. So I could have used other angles for starting place. I could have used other identities if I wanted a cosine wave. But let's illustrate it again just with a sine wave, which is how I've written your homework number 10. Let's try something like y equals, and let's do a sine cosine wave, but let's use some different numbers. How about, let's try 2 times sine of 3x minus 5 times the cosine of 3x. So let's try a harder one here. The technique that I showed you still works. You're going to manipulate this with a squared plus b squared, except here the a is 2 and the b is 5. Whether you call it 5 or negative 5, we could be flexible on that. Depends about the identity we're going to use. Let's call it 5 right now. Okay, can I turn this into a single sine wave? Let's get out the a squared plus b squared, square rooted. What do I get? Square a, I get 4. Square b, I get 25. 4 plus 25 is 29. So that's going to create a funkier number right there. That's okay. Let's rewrite this problem by multiplying by root 29 on the outside. And at the same time, dividing by root 29 on the inside. Sine 3x times 2 over root 29 minus cos 3x times 5 over root 29. Notice I kept the minus sign in the same position. I could have said plus here and minus 5 over root 29 there. Now, what am I aiming for? Let me get another colored pen out in front of us because we're just going to wrap this up today. This will be our last calculation. I'm trying to create the sine of A, cosine of B, minus the cosine of A, calling the A 3x, sine of B. And I'm hoping that the cosine of B is 2 over root 29 and the sine of B is 5 over root 29 is actually going to give me an angle. Now I have the sine cos plus or minus cosine here. So this is going to be the sine of A minus B. I'm using that minus sign there. So the formula says there's a minus sign there. Don't forget that there was a square root of 29 out here. That's going to be like my new amplitude. Different than the first two amplitudes. Here's amplitude 2, here's amplitude 5. 29, square root of 29, you're going to work it out. I can ask my calculator. Sounds like about 5.4. I'm not sure, but let's try it. Sorry. What's the square root of 29? Okay, just about 5.4. 5.38 and change. But I'll let the calculator keep track of the number. So what's my angle right here? The A is a 3x. So notice I have a period of 2 pi over 3, period of 2 pi over 3. And these two waves, two waves of the same period, that's important. Then I create another wave of the same period, 2 pi over 3. Well, what's this angle that I'm subtracting, this B I'm going to have to draw this angle B here. It's got a cosine of 2 over root 29 and a sine of 5 over root 29. Let me move my paper. Now that means like cosine, adjacent over hypotenuse, sine is opposite over hypotenuse. So let's draw a angle with adjacent side 2 and opposite side 5. That's not a perfect scaling, but that's not too bad. That would make this hypotenuse square root of 29. Now, unlike the last problem, that is not a famous triangle. I don't know that triangle by name. I could say that here's the triangle. Could say the triangle is like the inverse cosine of 2 over root 29. I could look up what that is on the calculator if I wanted to calculate it. And be careful whether you're thinking radians or degrees, but for the moment, let's just call it the inverse cosine of 2 over root 29. And let's ask the calculator about what that is. What does it look like here if I've drawn it? I tried to draw it reasonably, right? It looks like more than 60 degrees to me. This could be 70, 75 degrees. I think a little bit shy of 75. Now, the problem is I got to talk about degrees or radians. So since I naturally think in degrees, let's first do it in degrees because I'm thinking it's a little bit over 70 degrees. Say cosine inverse, 2 divided by square root of 29. Okay, I was a little shy. It's not quite 70 degrees, but 68.19 degrees, 68.20 degrees. But what is it in radians? Let's do it in radians just to get a feeling for that. Mode, switch from degrees to radians. And just repeat the same calculation by hitting second function entry. 1, I got 4 digits here. Give me 4 digits right here. 1.190. But this would be radians. That's not an obvious fraction of pi, so I'll just take it as it is. Okay, so now it's time to graph this puppy. Let's graph the square root of 29 times the sine of 3x minus this expression. You know, I don't have to do anything for my calculator except type this expression in. Calculator's going to do these calculations. Let's compare that to 2 sine 3x minus 5 cos 3x. Now we're at the top of the hour here, but this will just take us a minute to type in. It's kind of pretty to see these match. Okay, let's go back to here. Let's erase some of this other stuff. Sorry. Let me leave the y3 as y1 plus y2 in there because I'll let the calculator add them. And then I'll type in the thing that we calculated right here. Square root of 29 times the sine. But notice this time it's 3x with a subtract goofy cos inverse 2 over root 29. Subtract goofy cos inverse 2 divided by square root of 29. in the square root, in the cos inverse, in the sine argument. Okay, that spills out on the screen, right? But I think I typed in everything correctly. Now up here, let's type in the 2 sine 3x. And here, let's be careful with this minus sign. Let's type in the minus 5 cos 3x. Oh, I got to use the minus key on the bottom row. The opposite key, 5 cosine 3x. Same argument. Now, let's do the same coloring trick. Let's first turn off the sum. Let's graph ours and then see if the sum matches ours. I don't know about my window. Well, let's just run this thing out here with the window. Okay, this is going to fail badly because that has amplitude 2, and here comes amplitude 5. So I think I got to replan my window. Stop it. Do you know that you can stop any calculation you're doing just by hitting the enter key? And what happens is up here, the circle is like blinking at you, even on the old style calculator. What you did is you paused the calculation and hit the enter key again, you'll just restart the calculation. If you want to terminate this, hit the on key, and that just stops it dead. No little circle here in the upper right. I want to terminate this because I got bad amplitudes, right? So I want amplitude of 2, amplitude of 5. What was root 29? About 5.4, almost. So let's run this window. I guess I'm not upset about the amount of x I had, but let's run this window from -6 to 6. Okay, now let's try it. And let me get this a little bit closer to the camera for you. Okay, here comes my sine wave of amplitude 2. And it's got many periods in 0 to 2 pi. Here come my cosine wave of amplitude 5. I hope I have room for the other one. Look at the other one. Its amplitude is just slightly larger. And that's about the 5.4. So it doesn't seem to be very fancy different, just slightly different in amplitude, right? Now I'd like to draw the sum over the top of these, see if they match. But before I do that, I'm only going to pull out this time 1 period. What would 1 period be? 2 pi over 3? So let's run this, turning on the sum of the two functions. And now it's turned on. And let's run the window from 0 to 2 pi over 3. Sorry, 2 pi divided by 3. Okay, good. X scale, let's set 2 pi over 3, 1 pi over 3, pi over 6. Let's just set it to pi over 6. Well, that's probably not as critical. And let me give another unit. How about -8 to 8? A little more space in the y-axis. Okay, let's see what we got. I just want one wave, so I'm not asking for too much. Here comes the 1 cosine wave, which by the way is upside down of amplitude 5. Here comes the sum of these two waves. So first the calculator is drawing the sum really slow. And then it's going to draw my function in green. And I'm hoping the green shows up over the top of the black. Here it comes. There it is. There's the green showing up right there. It's going right on top of that black function. So the green thing that we wrote was correct. I'm going to move it over to the side. This function right here with a funny phase shift. What's the phase shift right here? Phase shift is when I set this argument equal to 0. So the phase shift would be x equal 1/3 cosine inverse of 2 over root 29. We did succeed in writing the sum of a sine and cosine wave as a single sine wave with a new amplitude and a shifted starting place. Okay, we're at the end of our time. I'm going to go see if I got this video straight and get it uploaded. I think everything's working. I'll copy these pages so that you can look at them again, but I sent you to the example 4 in section 6.4 because that's where you see him doing this also. And we're gonna call it a day right there. Now, I don't know how to turn this stuff off, so if I just abruptly kick you out of the room because I'm on a different equipment, don't worry about it. I'll see you again on Wednesday.